said a 1.5 kilohertz AC signal at 30 volt is connected across a 100 microfarad capacitor. Calculate the capacitive reactance. What is the current in the circuit? Can you try this? Pause the video and try. So now let's do this. Let's draw the circuit diagram for this question. So let's draw our capacitor there. It's our capacitor connected to the AC source. So from the question given to us, we have our frequency here. Our frequency is 1.5 kilohertz. Kilo, you know what kilo means? That is 1000. So I want to convert that later. We just multiply that by 1000 to eliminate that kilo out from there. So our voltage is 30 volts, and our C, the capacitance of the capacitor is C is equal to 100 microfarad. That micro is 1 million. That is 10 raised to the power minus 6. When you hear micro, 10 raised to the power minus 6, micro, you divide by 1 million. So when you multiply by 10 raised to the power minus 6, you eliminate that micro from there. So calculate the capacitive reactance. Now our capacitive reactance is given with this equation 2 pi Fc. Now this will now give us 2, this is our 1, 2 multiplied by 3.142, our frequency is 1.5 kilo, multiplied by 10 raised to the power 3, multiplied by our C, 100 microfarad. So 10, then 100 multiplied by 10 raised to the power minus 6. So when you press your calculator, all these will give you 1.06 ohms. 1.06 ohms. So this is the first part of that question. While the second part, what is the current in the circuit? I haven't calculated your capacitive reactance. That is your resistance. That's your resistance offered by the capacitor. We can now calculate our current using that idea. Current V is equal to current multiplied by our capacitive reactance. So our current in this case now be V divided by capacitive reactance. Our V from the question volt is 30 divided by what we have calculated there, 1.06, and that will give us 28.3 ampere. So now let's look at impedance Z. Impedance. Now what is impedance? We say impedance, this is the total opposition to the flow of current offered by an inductor, capacitor, and resistor. So when these combine together, so the total opposition they offered is known as impedance, represented by the capital letter F. So at times it can be a resistor and a capacitor in a circuit. So when resistor and capacitor also oppose the flow of current jointly, it is also called impedance. And where a resistor and an inductor in a circuit oppose the flow of current jointly, it's also impedance. So that leads us to the arrow. Let's take them one after the other. We have what we call the ROC circuit. ROC circuit. Now the ROC circuit is a circuit of resistor and capacitor connected in series in an AC circuit. So when you have such a circuit, connected circuit, call it ROC circuit. So when you have your resistor, for example, connected to your capacitor like this, to an AC source, so this circuit, this connection is known as a ROC circuit. The ROC circuit. So the opposition, that is the resistance, the total opposition, that is resistance offered by the resistor and the capacitor, can be calculated using the equations Z is equal to the square root of R plus the square of your capacitive reactance. So this will also give us R square plus 1 over 2 pi SC. All this also raised to power 2. Take note of that. Take note of that. Now, because of this capacitor that is there, there's what we call the phase angle. So the phase angle between the current and the voltage. And there will be a phase angle between the current and the voltage, because we are having a capacitor connected in a series there. So, and what will be the phase angle is given by the relationship times of the phase angle is equal to your reactance over your resistance, capacitive reactance over your resistance. So that is to say that the phase angle now will not be given by arctan, capacitive reactance over your resistance. So can use that to calculate the phase angle between the current and the voltage in an ROC circuit. The ROL circuit. The resistor and the inductor are connected in series. In an AC circuit, we call it the ROL circuit. Here, there is a resistance that is offered jointly by the resistance and the inductor. And that resistance can be calculated using Z is equal to the square root of R square plus SA square. Take note of that. So this is Z is equal to R square plus 2 pi FL square as well. So take note of that. Also, the phase angle between the voltage and the current is also calculated using the relationship. Tag of the phase angle is your reactance over resistance. So your inductive reactance in this case over your resistance give us the tang of this. So from here, the phase angle cannot be calculated using arctan inductive reactance divided by your resistance. So take note of that. So let's see the ROLC circuit. So the ROLC circuit is a series connection of your resistor, inductor, and your capacitor. So when the three are connected in series and in an AC circuit, we have what we call the ROLC circuit. And there are some things I want us to note here. You see, the ROLC circuit, we have the same current flowing through them. The different voltage passing through them. So here I want us to know that the voltage across this resistor is, let's represent that with our VR. Then the voltage across the resistor, VL. Let's represent that by VL. Then the voltage across the voltage across the inductor as VL. The voltage across the capacitor as VC. Take note of that. Then the total opposition to the flow of current in this case also, the impedance can be calculated using the square root of R square plus inductive reactance minus your capacitive reactance, all this square as well. Take note of that. Can use that to calculate the. So that is to say, this can also be R square plus 2 pi F L minus 1 over 2 pi FC, or this square, whichever. Then the phase angle in this circuit is tan alpha is equal to your reactance as well. Your reactance in this case would be SL over XC divided by your R. So that is to say our phase angle will now be the arc tan in bracket SL minus XC close bracket divided by your R. Take note of this. So here you are having another question. It said a resistor of 200 ohms is connected in parallel with a capacitor of 0.5 microfarad to a supply of 2500 Hz and a voltage of 10 volts. What currents flows in the circuit? Now for us to do this, let's draw the diagram, the circuit diagram for this. Let's draw the circuit diagram for this. We have our capacitor there. Let's connect it this way. Connected in parallel to a voltage source. Good. This is our capacitor. For the question is given to us to be 0.5 microfarad, and our resistor here is given to us to be 200 ohms. 200 ohms. Then our voltage is 10 volts here, while our frequency 10 volt. Our frequency is 2500 Hz. We are now asked to calculate the currents flowing in the circuit. Now, because the circuit is connected in parallel, we have different current. The current that will flow through the capacitor will be different from the current that will flow through the resistor. Take note of that. The current that will flow through the capacitor will be different from the current that will flow through the resistor. But there's a relationship that says the square of the current in the circuit will be the square of the current that will flow through the resistor plus the square of the current that will flow through the capacitor. So take note. Now we know that our current that flows through the resistor will be the voltage over resistor, and the current that flows through the capacitor will be our voltage divided by our capacitive reactance. We know our voltage is V, which is 10, because they will have the same potential difference. The voltage across the two components is the same, 10 volt, because they are connected in parallel. So devices connected in parallel have the same voltage. They have different current flowing through them, but they have the same potential difference across them. So having known, so can use that idea, that knowledge to calculate our current flowing through the resistor. So we know the voltage because we already know the resistance of the resistor. So here our I arrow, bringing that down over arrow, this will be 10 over our resistance, which is this. So the current here, when you press your calculator, will be 0.05 ampere. So that is the current that's flowing through the resistor. Now for us to know the current that is flowing through the capacitor, we must, since we know our voltage, we must know our capacitive reactance. So let's look for capacitive reactance first. So we have our capacitive reactance will be 1 all over 2 pi Fc. So that is 1 all over 2 multiplied by 3.142 multiplied by our frequency is 2500 multiplied by our capacitance 0.5. Don't forget microfarad multiplied by 10 raised to the power minus 6. So when you press your calculator and you divide this, you are going to get 127 ohms. 127 ohms. Going to get 127 ohms as our our capacitive reactance. So take note of that. Now, having known our capacitive reactance, we can now place it here to get our, when we place it here, is to get our, we know this to be 10 and we know this to be 127. When you divide that, we have a current that is flowing through the capacitor. And when you know your current flowing through the capacitor, we now use the relationship. You already know this, we have calculated this to be this. Then current, whatever we get here, we put it here. So you now calculate, that will be the current that flows in the. So now let's calculate that now using our, so calculate our current that flows in the capacitor. I'm going to use V over capacitive reactance. So we're going to use V over capacitive reactance, and that will give us 10 divided by our capacitive reactance, which we have calculated to be 127. So when you divide that with your calculator, you are going to get 0.079 ampere. That's what we're going to get from there. So having known our current in the current that flows through all these devices, we can now use our relationship, the main current square, the current across the capacitor square, plus the current across the resistor square, plus the current across the capacitor square. So our main current will now be equal to the square root of all this. So that will give us, so this will give us 0.05 square plus 0.079 square. So calculated there. So if you do this, actually, when you press your calculator, you are going to get 0.0935 ampere, which is still the same thing, nonsense. 93.5 milliampere when you multiply by 1000. So this is another question. It says an inductor of 0.012 Henry, a capacitor of 8 microfarad, and a resistor of 100 ohm are all connected in series, and an AC voltage of 5 volts, that is the RMS voltage 5 volts, and frequency 200 Hz is connected to the arrangement. Calculate 1. The reactance of the capacitor and inductor. 2. Impedance of the circuit. 3. RMS current flowing. So you can pause the video and give this question a try. Pause the video and try it. Now let's draw the circuit diagram for this question. We have a resistor, we have our inductor, then we have our capacitor, all connected in series to our AC source. Now here is our resistor, inductor, capacitor. So this is an ROSC circuit. Then our resistance in the circuit is given to us to be 100 ohms. Our inductor is 0.012 Henry, while our inductance is 0. This Henry. Our capacitance in the side 8 microfarad. It is given to us there. Our capacitor in the circuit is 8 microfarad. The question says, what is the reactance of the capacitor and the inductor? So the first thing we are calculating here is the reactance of the capacitor. That is capacitive reactance, and that is given by, so let's do the first one. XC is equal to 1 all over 2 pi FC. So that is what we are using. So this will give us 1 all over 2 multiplied by 3.142 multiplied by our frequency from the question is given to us to be 200. Our frequency is 200 Hz multiplied by our capacitive reactance. Capacitive reactance is 8 microfarad multiplied by 10 raised to the minus 6. So when we press our calculator here, we are going to have 99.5 ohms. 99.5 ohms. That is our capacitive reactance. Now, having known our capacitive reactance, the second part says you calculate the inductive reactance, and that will be given by SL is equal to 2 pi FL. That will be 2 multiplied by 3.142 multiplied by our frequency from the question, which is 200, multiplied by our capacitive and our inductive reactance from the question is 0.012 Henry. 0.012 Henry. When you press your calculator, you are going to have 15 ohms. Since we are calculating resistance, we are going to have 15 ohms. Now that we have calculated our capacitive reactance and inductive reactance, we can now calculate the second part here. We can now calculate the impedance of the circuit using the relationship Z is equal to the square root of your resistance square plus into bracket inductive reactance minus capacitive reactance, all this square. So this is what we are going to use. So here that will give us 100 square plus into bracket. We calculated this to be 15, approximately 15 minus 99.5, all this square. So here we are going to have 10,000 plus 84.4 square, because we can't have that. So this will now give you the square root of 17,123 plus 3, 130.9 ohms. So this is the whole opposition, whole resistance in the circuit. That's the resistance in the circuit. Now from all this idea now, we cannot calculate the current. Having known the resistance in the circuit, we cannot calculate the RMS current flowing in the circuit. We cannot calculate the RMS current flowing in the circuit and the RMS current flowing in the circuit. So this is our number 2. And the last part, which is number 3, the RMS current flowing in the circuit will now be our voltage divided by our resistance, total resistance in the circuit. So current flow in circuit, our voltage in the circuit is going to us to be 5 divided by 130.9. So that will give you 0.038 ampere.